Signals and Systems, CT Fourier Transforms, Part 3, Transform Pairs, Series on Signals and Systems, Lecture number 3.13. Continuous time Fourier Transforms. They are useful to show the frequency content of non-periodic time domain signals. In the present session, we focus on certain commonly used standard signals to find their transforms, to know their frequency content. Signals to be considered in this session are impulse function, step function, triangle function, pulse function, etc. Now, with this small introduction to the session, let us move to the actual session. Before going to finding the transforms, let us consider the transform definition, CTFT definition. The Fourier transform f of omega, it is called spectral density function. For a CT non-periodic signal, f of t is, f of omega is integral minus infinity to plus infinity f of t e power minus j omega t dt. It is analysis equation. It is also called forward transform. Reverse transform is also there. F of t is equal to 1 by 2 pi integral minus infinity to plus infinity f of omega e power j omega t d omega. One can notice forward transform gives frequency content of the signal, or it converts time domain signal into frequency domain, whereas reverse transform converts frequency domain signal into time domain. These are defining relations or expressions. We are going to keep these expressions in the background of our minds while finding the transforms. To begin with, we consider impulse function. Fourier transform of impulse function is 1, and Fourier transform of 1 is 2 pi delta of omega. It says impulse function and 1 Fourier transform pair, and 1 2 pi multiplied by impulse function. These two are another transform pair. How this relations have come into being? For that, consider Fourier transform of delta of t using the defining relation forward transform. It is integral minus infinity to plus infinity delta of t e power minus j omega t dt. So this integral becomes equal to 1. Therefore, delta of t 1. These two are transform pair. Using symmetry property or duality property, the second one can be obtained, this one. We consider another pair. Fourier transform of e power j omega naught t is 2 pi delta omega minus omega naught. How this relation has come into being? Fourier transform of 1, we have seen already, it is 2 pi delta of omega. Using frequency translation theorem, frequency shifting property, Fourier transform of 1 into e power j omega naught t, it is 2 pi delta omega minus omega naught. Thus, e power j omega naught t, its Fourier transform becomes 2 pi delta omega minus omega naught. Notice we are using properties, various properties of Fourier transforms plus defining relations of Fourier transform, in deriving, in finding transforms of various functions. Properties, they are discussed in a previous video. Those who have not gone through that video, 2, CTFT 2, you may go through it. Now we consider impulse train. In the previous slide, it is a single impulse. Now it is impulse train, a periodic signal. The Fourier transform of impulse train delta t of t is omega naught delta omega naught omega. So to know how this particular relation has come into being, consider the signal delta t of t represents a sequence of equidistant pulses of unit strength and separated by t seconds. Time period is t, capital T. Mathematically, therefore, it can be denoted as delta t of t equal to sigma n minus infinity to plus infinity delta t minus nt. As it is a periodic signal with the period t, we can express it as Fourier series. Delta t of t, it is minus infinity to plus infinity fn e power jn omega naught t, where fn is exponential Fourier series quotient equal to 1 by t integration over one time period delta of t e power minus jn omega naught t dt, and it can be found equal to 1 by t. Thus, delta t of t is 1 by t sigma minus infinity to plus infinity e power jn omega naught t. Taking Fourier transform both sides, apply Fourier transform both sides. It becomes 2 pi by t minus infinity to plus infinity over sigma delta omega minus n omega naught equal to omega naught minus infinity to plus infinity delta omega minus n omega naught equal to omega naught delta omega naught omega. Hence, we can notice that the Fourier transform of a unit impulse train of period t is also a train of impulses of strength omega naught separated by omega naught radians. This is one impulse train in time domain. This is another impulse train. Of course, it is in frequency domain. So Fourier transform of impulse train is another impulse train. Now we consider trigonometric functions, cos and sine. What is Fourier transform of a cos function? Let us suppose f of t is cos omega naught t. Then Fourier transform f of t, f of omega is equal to limit tau tends to infinity integration from minus tau by 2 plus tau by 2 cos omega naught t e power minus j omega t dt. Now cos omega naught t, it can be expressed as e power j omega naught t plus e power minus j omega naught t by 2. E power minus j omega t can be taken inside, and a little bit of manipulation results in limit tau tends to infinity tau by 2 sine omega minus omega naught tau by 2 by omega minus omega naught tau by 2 plus sine omega plus omega naught tau by 2 by omega plus omega naught tau by 2, which is equal to limit tau tends to infinity tau by 2 sample function omega minus omega naught tau by 2 plus sample function omega plus omega naught tau by 2. It results in pi multiplied by impulse at omega naught, another impulse at minus omega naught. Therefore, Fourier transform of cos omega naught t is pi times delta omega minus omega naught plus delta of omega plus omega naught. In the similar way, Similar manner, one can find Fourier transform of sine omega naught t as j pi multiplied by delta omega plus omega naught minus delta omega minus omega naught. Now we consider one-sided trigonometric functions, sine and cos functions, to find their Fourier transforms. Find Fourier transform of cos omega naught t u of t and Fourier transform of sine omega naught t u of t. We use frequency convolution property or theorem to solve the problem. This theorem essentially says multiplication in one domain is equivalent to convolution in another domain, or convolution in one domain is equivalent to multiplication in another domain. According to this theorem, F1, F2 product, its transform is convolution of their spectral density functions, of course multiplied by 1 by 2 pi. Now consider F1 of t as cos omega naught t and F2 of t as unit step. We know in the previous slide it has been shown F1 of omega equal to pi delta omega minus omega naught plus delta omega plus omega naught, and F2 of t as pi delta of omega plus 1 by j omega. This is Fourier transform of unit step function. Therefore, using the relation Fourier transform of F1 into F2 is 1 by 2 pi F1 convolution F2. It becomes equal to pi by 2 pi into delta omega minus omega naught plus delta omega plus omega naught convolution with pi delta of omega plus pi by 2 pi delta omega minus omega naught plus delta omega plus omega naught convolution with 1 by j omega. Using the facts that same function results when it convolves with the unit impulse and the shifting property of the convolution, one can do further manipulation of the expression for Fourier transform of F1 of t multiplied by F2 of t. It gives pi by 2 delta omega minus omega naught plus delta omega plus omega naught plus of 1 by j omega minus omega naught plus 1 by j omega plus omega naught. In the same way, one can find Fourier transform of sine also. Sine omega naught t u of t equal to pi by 2j delta omega minus omega naught minus delta omega plus omega naught plus omega naught by omega naught square minus omega square. Now, unit step function. Fourier transform of unit step function, it can be found as 1 by j omega plus pi delta of omega. Actually, we used this result in the previous slide in finding Fourier transform of trigonometric functions multiplied by unit step. Now we consider unit step function to find its transform. Let u of t is half plus u of t minus half, which is expressed as half plus x of t. So x of t here is u of t minus half. Now Fourier transform of u of t is Fourier transform of half plus Fourier transform of x of t. But dx by dt is delta of t. Differential of step is impulse. From that we got this equality, and Fourier transform of delta of t is 1. Now j omega x of omega is 1 from differentiation property. So it results x of omega is equal to 1 by j omega. Now Fourier transform of u of t equal to Fourier transform of half plus Fourier transform of x of t. For half, Fourier transform is 2 pi by 2 delta of omega. For x of t, it is 1 by j omega. Ultimately, we got the result as 1 by j omega plus pi delta of omega. Gate function. It is a rectangular pulse whose transform is sample function. Fourier transform of a g tau of t. This is time domain gate function. The transform of this function can be shown as a tau sample omega tau by 2. Here the gate function g tau is defined. A g tau of t means it is equal to a for mod t less than tau by 2 and it is 0 for mod t more than tau by 2. It's a Fourier transform. F of omega becomes equal to integral minus tau by 2 a e power minus j omega t dt. Integration can be done and a little bit of manipulation leads us to the expression a tau sample omega tau by 2. Note that the transform is real. Another function we consider, that is decaying exponential. Fourier transform of the product e power minus at u of t, it is 1 by j omega plus a when a is positive. This can be proved by considering Fourier transform defining relation. F of omega, it is minus infinity to plus infinity over an integral sign e power minus at u of t e power minus j omega t dt. It is equal to 0 to infinity e power minus at e power minus j omega t dt. Now performing integration and substitution of the limits leads to f of omega being equal to 1 by a plus j omega. The answer is Fourier transform of e power minus at u of t is 1 by a plus j omega for a positive values. Notice the limits, they are changed from minus infinity to plus infinity to 0 to infinity. Reason is, here unit step is there. Unit step is 0 for negative values of time. Therefore, minus infinity to 0, the entire function becomes 0. We consider another exponential e power minus a mod t. Its Fourier transform can be shown as 2a by omega square plus a square for positive values of a. Fourier transform, its Fourier transform is minus infinity to plus infinity e power minus a mod t into e power minus j omega t dt. Now the limits, integration limits can be split into two, minus infinity to 0, 0 to infinity. So we have two expressions. And integration can be performed and a little bit of manipulation can be done, resulting in an expression 2a by omega square plus a square as the Fourier transform of e power minus a mod t. Another important function or signal, triangular signal or triangle function. Symbol for triangle function is delta. Delta tau of t. Its Fourier transform can be shown as tau by 2 sample square omega tau by 4. Using duality property or symmetry property, one can also show that Fourier transform of w by 4 pi sample square wt by 4. For this transform is delta w of omega. Here basic point to be kept in mind is, for triangle function, transform is sample function square. For sample function square, Fourier transform is triangle function. Now let us see how this relation has been arrived. This relation can be derived easily using time convolution theorem and the fact that convolution of two same gate functions of duration tau results in a triangular signal with duration 2 tau. If the amplitude of the gate function is a, then height of the resultant triangular function becomes a square tau. Now this information is used in the derivation of Fourier transform of triangle function or sample function square. According to time convolution property, Fourier transform of convolution of two time domain functions. It is product of their spectral density functions. Let f1 of t is equal to f2 of t is equal to the gate function a g tau of t. Then f1 of omega, f2 of omega both becomes equal to a tau sample omega tau by 2. But f1 of tau convolution with f2 of t, but f1 of t convolution with f2 of t, it becomes a g tau of t convolution with a g tau of t. It becomes equal to a square tau delta 2 tau of t. Therefore, Fourier transform, its Fourier transform is a tau sample omega tau by 2 whole square. Ultimately, we can notice delta tau of t, its Fourier transform is tau by 2 sample function square omega tau by 4. Using the duality property, the second relation can simply be written down. Now we consider signum function to find its Fourier transform. Fourier transform of signum of t can be shown equal to 2 by j omega. One can also find Fourier transform of 1 by t as minus j pi signum omega. How to get these results? Here it is given. We can observe that signum of t is 2 u of t minus 1. Here u of t stands for unit step function. Considering the Fourier transform both sides, Fourier transform of signum t is Fourier transform of 2 u of t minus 1. For unit step, we know Fourier transform. For 1 also we know Fourier transform. So substitution gives this expression. Manipulation, simplification gives us it as 2 by j omega. Using symmetry property or duality property, the second relation, this one, can be easily obtained. Now impulse differentiation. Nth differential of delta of t, its Fourier transform can be shown as j omega over n. Using duality property, second relation can be written. Fourier transform of t power n is 2 pi j power n nth differential of delta of omega. Applying a time differentiation property, that is Fourier transform of nth differential of f of t is j omega power n f of omega to impulse function, we get the first relation. It is direct application. Now apply symmetry property or duality property to get the second relation. Now we have come to the end of the present session. Let us recollect briefly whatever all we discussed in the present session. Mainly, this session is meant for finding or knowing Fourier transforms of standard signals like impulse function, like a pulse function, like a triangle function, like trigonometric functions, and we considered all those functions and determined their transforms. Hope this session is useful to you. We meet again in another session with another topic soon.